Hello there, cutie patootie, math angel. Welcome back. This is Decaf-Math ASMR. Thank you for choosing to spend some quiet time with me right here and right now in our little math nook. I hope that you're doing well as can be. Today I am going to be looking at this integral in the context of improper integrals. And this was a requested concept to go over both recently as well as in some of my older videos. So I'm glad to finally be able to start this conversation here. So I hope that if you are reviewing this, that it's a nice, no pressure way to review or quiz yourself, or if nothing else, maybe get a little bit of encouragement in your studies. But of course, as always, even if you don't care about math at all, or if you don't feel like studying right now, I hope that you can feel free to just sit back, close your eyes, maybe even drift off to sleep if you need the rest. Maybe you'll even catch a tingle or two along the way. I'll be kind of soft speaking and drifting in and out of a whisper as well, like this throughout the entire video. So I just hope that this blesses you in some way. I know I'm always blessed when I'm able to take a quiet moment here. So I'm very grateful for our Decaf-Math space. So let's take a look at this question. Let me just read it out loud first. So we have the integral of -3 over x squared with respect to x from 1 to infinity. And since this is just kind of like a little decaf session, I'm just going to say whatever comes to mind that I think might be helpful. So feel free to just go at your own pace. I just want to make sure that we're building on other concepts and just making sure that we're on the same page here. So if I'm moving too quickly or too slowly, do feel free to adjust the pace here, okay? But again, this is never really like a formal lecture. I'm just here to be your math friend and encourager, so yay you. So what makes this an improper integral? Well, in this particular case, it is because we have this infinity that it's improper, so to speak. So what does that mean? Well, basically, hopefully if you're learning about this, that you've already learned about integration, what it means in terms of being the area between our curve or function and the x-axis over a particular interval, right? It's an infinite sum. And so you've learned about what an integral basically is, about Riemann sums, and then hopefully you would have learned some basic integration techniques, right? Like our basic antiderivative rules that are the opposite of our derivative rules, and perhaps some u substitution, integration by parts, or using some trig substitution. Maybe you've learned some approximation methods, that kind of stuff. So those are just some techniques that we come back to time and time again as we work with integrals. But I should point out that not all integrals can be solved with those methods. Those are just some tools for our toolbox, but sometimes all we can do is approximate or just leave things be. There's nothing to be done. But this is just a group of integrals that are improper. They have a particular form. It's kind of weird to look at. In this case, we have an infinity here, so it's kind of strange to deal with based on the techniques that we've already covered, but with just a few definitions and a little bit of analysis here, we can actually calculate this particular question. So let me show you why I decided to bring up our old integration techniques, and that's because math always builds on itself, right? So we don't want to forget those, so let's make sure that we are okay with that. But I just want to encourage you that if you happen to be struggling with the particular unit, say this. Sometimes it's the concept right in front of you, and sometimes it's just that you have to go back and review integration, right? So I often say that here. You might just want to give up, but sometimes it's actually an old concept to brush up on, or just to fill in a little gap and you're good to go. It might not be just because of the question right in front of you. Just stating the obvious, but I know when we get caught up in our work, it's sometimes hard to see the forest for the trees. So I did want to encourage you with that, but along those lines, I was going to say that this question actually can be, even though we can't directly solve this with an infinity like that, it's very similar to a question that you probably would know how to do if you're comfortable with basic integration, which is if I have a 1 and let's say just any other number, so let's just say 2 of this, the same function with respect to x. If I gave you this question and you're comfortable with basic integration, you could probably solve this without too much trouble. Of course, if you need to pause and take your time, do feel free to do so, but I'm going to go ahead and calculate it here because I'm going to make a point. So I'm rewriting this in this form, bringing the 2 up away from the denominator so that I have this form x to the power of a constant n. And that's because this is a basic antiderivative that we know, which is that the integral of x to the power of some constant n, as long as the variable's on the bottom, is x to the n plus 1 over n plus 1. It's just the backwards of our power rule. I have other videos on this if you want to check that out, but as long as this isn't x to the negative 1, because the integral of 1 over x is going to be the natural log. But for this case, we can use this. So the negative 3 is just a constant that can be pulled off to the side. And we have x to the negative 2 plus 1 is negative 1 over negative 2 plus 1 is negative 1. And then I put my 2 bounds, so 1 and 2. 1 and 2. And then I just simplify this so the negatives cancel because we're multiplying. 3, the 1 on the denominator, doesn't really matter, 3 over 1. So 3 times x to the negative 1 is just 3 over x. And we go from 1 to 2. So basically I calculated the antiderivative of this inner part. If you're familiar with the fundamental theorem of calc notation thing, we're talking about capital F. So here we have 3 over x is our antiderivative, and then we just want to plug in the upper bound, so capital F of 2 minus capital F of 1. But basically you just plug in the upper bound and then subtract, and then whatever you get when you plug in the lower bound. So here I would get 3 over 2 minus 3 over 1. And if your function happens to be more complicated, that's okay, as long as you can find this antiderivative, plug in the upper bound. Everywhere you have x, put in that 2, and then minus, and then put a parentheses, and then put a 1 everywhere you have an x, and then simplify. So in this case, I'll just clean it up. Common denominator of 2, 3 minus 3 times 2 is 6. So hopefully this is the right answer. I should have written this out right. But this is still a very straightforward integral. get a nice clean answer, and pretty much the basic concept here is to find this antiderivative, plug in the upper bound, plug in the lower bound, find the difference. And so what this means is that on the interval from 1 to 2, the area between this function and the x-axis nets to be negative 3 over 2. So if this entire function is below the x-axis on this interval, then the area is 3 over 2, but it's below the x-axis. But if, for whatever reason, this function is partially above and partially below on this interval from 1 to 2, then this just means that there's more area that's below the x-axis than there is above, because this net's negative 3 over 2. But that's the general idea here. And we just do upper and lower bound. And if we have no bounds at all, it's just an indefinite integral, just open. So we would just do 3 over x, and then don't forget to put a plus c to represent any constant, because when we take the derivative of this, the derivative of constant is 0, that would go away, and we would still get negative 3 over x squared. So why do I mention all of this for this question, right? Why are we doing this whole definite integral thing with bounds? Well, for this, it's similar, but conceptually there's a little issue with this infinity. So if I were to treat this like every other integration problem like this, I would get to this step, and I might get to the antiderivative of this is 3 over x, and then I might try to plug in this upper bound and do 3 over infinity minus 3 over 1, upper minus lower bound. But we cannot just divide by infinity. We mentioned this in an end behavior video not too long ago, but infinity is not a number, right? We can't just divide it like it's a number. So that's why this is improper for this particular question, is there just is a problem with just doing a regular integration as we've done it so far. We can't just do this, but there's a little concept that we can consider here, which is this idea of limits, right? So much of calculus is based on this idea of a limit, and that's exactly what we're going to do here. So before we get into the direct formula here, let's actually look at what we are looking at. So instead of plugging infinity as a number, we are talking about a limit, but a limit of what? So for both of these, we are looking at our function y equals negative 3 over x squared. So I'm just going to try to sketch this. It's going to not be too precise, but I hope to get the general shape here. So if we have x and y, and normally you would put your tick marks in for scale, but I just want to get the general shape of this graph. So what does y equals negative 3 over x squared look like? Well, for one, when x gets really big, infinitely large, aka the end behavior, this entire denominator gets infinitely large and it's positive, and then 3 over something really big is going to approach 0, but it's always going to be negative, right? So x squared is never going to be negative, and so this is positive, but then the negative of that whole positive thing is negative. So it's approaching 0, but from a negative side. So that means that the end part of this graph, if I were to just kind of sketch it as a general shape, is going to approach 0 as x gets really large. It's going to keep going and approach 0. It's going to approach the x-axis but never touch it. Okay, and then on this part here, x is never going to equal 0. It can't equal 0 because we can't divide by 0. if x equals 0, we'd have 3 over 0. Dividing by 0 breaks math. So there's actually a vertical asymptote, meaning we'll never touch x equals 0 in our graph, but as x approaches 0, so this is going to get to be a small positive fraction, really, really small. When I do like 3 over 1 over a billion, for instance, that denominator has a fraction, so that billion's going to go back up to the top when I divide it. In other words, taking a piece and dividing it into infinitely small portions gives us infinitely many pieces. So that's going to be really large, but then we're going to have a negative large number. So this is going to be very, very negative, which is small, but in absolute value is very large. So that means that as x approaches 0, I approach negative infinity down here. And so it's going to have something like this. It's going to never touch the y-axis, but it's going to keep approaching it. And it's never going to touch the x-axis, but it's going to keep approaching it. And somewhere in between, there's going to be some kind of, curve like that. And I'm purposely not putting in tick marks here because I don't know exactly the shape of this. I just know it's round like this. If you want to be more precise, you're going to have to do a little more analysis, a little bit of calculus. Just do more calculations here that we don't have to do. But you can also plug in more values. So if x is 1, you have negative 3. So 1 comma negative 3 should be on here. If x is 2, you'd have negative 3/4. So that should be on there. And then etc. You can just pick more values, but you can see that this approaches 0 very quickly. If x is 4, you have negative 3 over 16. So it approaches it very quickly, and then as x gets really, really large, this approaches 0 from the negative side. And then this will be symmetric when x is negative as well. So as we approach 0 from the negative, it should also approach negative infinity, and same this way. As x approaches negative infinity, x squared is going to get infinitely large. This whole thing goes to 0 from a negative part. And anything squared is going to be positive, and x is not going to be 0. It's symmetric like this, or it should be. My sketch is kind of not that great, but I hope that you get the idea. And the whole point of sketching this out is that now I can visually see that from 1 to 2, this part's actually all going to be negative, right? We said that this is never going to be positive because the denominator is always positive, and so a negative divided by a positive is always negative. So that means that from 1 to 2, again with no scale here, but hopefully you get the idea, from 1 to 2, let's pretend, then this area between my curve and the x-axis is all below the x-axis, so this is negative 3 over 2. So this area is 3 over 2, but it's negative because it's below. So now that works for 1 to 2, but what happens if we're going to go from 1 to infinity? So that means that, what does that even mean? It means that the upper bound is infinity, right? That means that we're going to keep going from 1, so we're starting from 1, covering all of that blue part, and then we're going to keep going, and we're going to keep adding to infinity. And remember that this graph never touches the x-axis, but it approaches it infinitely. This is where things get really interesting, right? So you would think maybe, maybe if I keep going here, I'm always adding a little bit of an area. So is the total area infinity, or does it, what we call, converge to a particular value? So what we're going to do for this particular question is, instead of thinking of infinity as an actual number, because it's not, I'm going to replace it with a different variable. So I'm just going to call this upper bound capital N. Whatever we want. You can use T, you can use M, or whatever. I'm just used to N, so that's what I'm going to do. And then we're going to take the limit as that upper bound approaches infinity. So what I can do here is take the limit as N approaches positive infinity, my upper bound approaches positive infinity, but I'm going to replace that with N. So I'm going to do this entire integral with my upper bound of N, but then I'm going to take the limit as that capital N approaches infinity. And that's this idea. Does this area converge? So what this converge idea means is basically, without getting too deep into the analysis stuff, but basically it's, does this limit exist and is it finite? Is it just some kind of number? If you get a constant number, then you can write this. If you don't get a constant number, if you get infinity, negative infinity, or if the limit doesn't exist, then this area does not converge. Your integral is just divergent. And that's what you would say, just that the integral diverges. So let's just go ahead and calculate this then. Let's give it a try. So we already know that the antiderivative of negative 3 over x squared, just based on what we did earlier, is 3 over x. And so I'm just going to calculate that as usual. We have 3 over x from 1 to n. And then we'll do the limit later. So you plug in the upper bound and the lower bound. So the limit as n approaches infinity of 3 over n minus 3 over 1, which is just 3. And now, as n approaches positive infinity, this goes away. The negative 3 is still there, but this is 0, right? As n gets infinitely large, this part goes to 0. This is just a regular limit question from wherever, pre-calc maybe. And so this equals negative 3. And so in this case, the limit does indeed exist, and it's finite. And if we look at this from 1 to an infinitely increasing n, it kind of makes sense. Like this is negative 3 over 2 right here. And then we add smaller and smaller pieces here. I mean, I probably would never guess negative 3 specifically, but you can kind of see that as we keep increasing n, these pieces keep decreasing. And so it's kind of like the idea of 1.9999999 infinitely repeating is basically 2. Conceptually, you're taking the limit. This thing approaches 0. This area gets smaller and smaller. And so it does indeed converge to this sum. And so this improper integral is equal to negative 3. If somehow this limit, like I said, doesn't exist, or is infinity or negative infinity, it's not finite, then you would just say that this diverges. Okay? So for this kind of improper integral, we're basically talking about when the upper or lower bounds are infinity or negative infinity or both. And so all you do is, if it's an upper bound of infinity, for instance, just set a different variable and take the limit as that variable approaches infinity and do your regular integration however you can. If you have negative infinity, for instance, let's say you have negative infinity to, I don't know, just some number 6 of some function, then you're talking about this sum from negative infinity up to whatever, not this case, but in general. Then you can try out the limit as n approaches negative infinity of n to 6 f of x dx. So you get the idea? You just replace the bound with another variable and take the limit as that variable approaches negative infinity or positive infinity. And then of course in general you can use your other integration rules like flipping the bounds using negative, right? So if you flip a to b to b to a, you can just do negative. It really just depends on your question and what's given, but that's a general tip you can do, is the negative side, the positive side, again only if it converges, meaning that the limit actually is a number. And then the other point here is what happens if you have negative infinity and positive infinity. So if you have this situation of some function, then you can actually break this up based on our other integration properties, which is that you can just go from negative infinity to some other constant, any constant that you want, as long as it's still continuous here, and do this. So you break it up into a sum of the negative infinity to a of f of x dx plus a to positive infinity f of x dx. And then now you can do both limits. The limit as n approaches negative infinity from n to a of this, plus from a to n as n goes to positive infinity. So now you have two limits to deal with, but again, we still have to consider whether or not this converges. So if either of these do not have a finite limit, so if, like, let's say this one is infinity, then this limit or this integral diverges. So you don't even have to do this one. But if they both converge to a value, then this improper integral here is equal to the sum of the two. And then you just use each one. Okay? That's just the general idea here. So you just want to break this up into two. Other than that, you just want to use your regular integration techniques. It really depends on the functions that you're looking at, but I hope that this at least helps you build some intuition there, whether the area actually converges or not. And that pretty much covers this type of improper integral. So the kind where you have infinity or negative infinity or both in the bounds. You just want to do this limit idea and check for convergence. But there is another type of improper integral, and that would be not having infinity per se or negative infinity in the bounds, but instead some value of discontinuity. So if this question had like a 0 somewhere, then you can't just plug in. So it's basically whenever you run into issues trying to plug in the top and the bottom bounds, this would be undefined, so we'd have to do a different type of limit as well. But we'll look at another example of that another time. I just want you to be able to start considering this idea of, instead of just directly plugging in infinity, which you can't do as a number, you instead take a limit as the other variable, the upper bound or the lower bound, approaches infinity or negative infinity, or splitting it up into two. I hope that helps for the first type, and I'll see if I can make up an example for the discontinuity situation. But also, of course, having said that, when I talk about splitting the negative infinity to infinity, make sure your actual value of your constant isn't yet again another like discontinuous point. Just make it nice there. Okay, so again, hope this was helpful. If you are resting or asleep right now, I'm wishing you sweet, sweet mathy dreams. Thanks for hanging out with me, and I will see you around for more math very, very soon. Math and ASMR